let's apply that product rule to this example that we were looking at. Remember, this describes this function, the change of position s of a spring with time, some sort of decaying function as we saw. So what we do is we let the first part of the function equal u and the second part of the function equal v. So you need to identify what your two functions are and let one bit equal u, one bit equal v. It's not crucial that you get that the right way around, just so long as you call one u and one v. And then you apply the product rule, which is telling me I've got to take each bit and differentiate it. So if you're going to set it out, you could do worse than using to do halves of the page. So u, what's u? 2e to the minus 0.9t. And I've got to differentiate that to find out what du by dt is. And then v. What's v? Sine 10 pi t. And then I've got to differentiate that to find out what dv by dt is. Oops. Okay, so we need to find out what these differentials are. So referring to the table of common differentials that we wrote down a couple of weeks ago, if we look at the first one, it's the differential of an exponential function. So which rule is the one that applies? The exponential one, which is a e to the bx. So what do? The b comes down and multiplies by the number in front to give us a times b, and the power stays exactly the same. So in the example, minus 2 times 6 is minus 12, and the power stays the same. So in this example, what do we get? Two times minus 0.9 is minus 1.8. e to the minus 0.9t, so differentiated. The second one, dv by dt, this is a sine function, so we go to our table of differentials, and the sine function, sine changes to cosine, and the b, whatever number is inside, comes out and multiplies by the number in front. So the 10 pi, the number that's multiplied by the t, is all of this, the 10 pi. So that comes out and goes in front, and the sign changes to a cosine. So we get 10 pi cosine 10 pi t. Okay? Just practice. That's all these are. You've got to practice these little rules. And we've spent some time doing that already. So now we've got what we need for the rule. The rule tells us that the differential, the s by dt, because we're using s and t in this case, equals the first bit, u, which is 2 e to the minus 0.9t, times the differential of the second bit, which is 10 pi cos 10 pi t, plus the second bit, which is sine 10 pi t, times the differential of the first bit, which is minus 1.8 e to the minus 0.9t. Just about managed to get it on. Okay? If we look at it, we can see that this bit is u, this bit is dv by dt, this bit is v, and this bit is du by dt. So that's the rule. U dv by dt plus v du by dt. So now I'm going to try and tidy it up, because you know that's very untidy at the moment. It's correct, but it's not in a certainly a usable state. First of all, numbers go first, so I can actually, this part, this whole bit here, this bit, can be tidied up. The 10 can be multiplied by the 2 to get 20. So I'm going to put 20 pi at the start, and then I'll put the exponential number, and then we always put the wave function or the cosine trigonometric function at the end. Same here. I'm going to put the trigonometric function at the end, and so also take into account that this is negative, so that changes this whole thing to negative. So tidying up, I get ds by dt equals 20 pi e to the minus 0.9t times the cosine of 10 pi t minus 1.8 e to the minus 0.9t times the sine of 10 pi t. So now I've got it in a much more usable form. If we look again, you can see I put the 20 pi at the front. So you put numbers at the front, then other functions like the exponential function, finishing off with a trig function. Numbers, the exponential, finish off with a trig function. Common practice, because if I leave this here, for example, you wouldn't know whether it was a sine of the whole lot or just a sine of that bit. So now there's no confusion. So that's why we do that. Something else I would do, and it always happens when we've got exponential functions in here, because the power of the exponential function doesn't change, they are identical. So I can take them outside of the bracket. I can factorize. I look for what else can come outside the bracket. Well, nothing really. I could faff about with the numbers and take something out, but it's not really worth it. Pi is not common to both, so I'll take out the exponential term, e to the minus 0.9t, and then what's left is 20 pi cos 10 pi t minus 1.8 sine 10 pi t. And it's worth tidying up, because if at the end of the day you're going to be putting numbers into these, making it as straightforward as possible is beneficial. And that's the differential. Thinking about the exam scenario, you know, if you get part way with this and you get this correct, that's right. And then if you're tidying up, you know, we're sort of talking about addition to the grade that you're going to get, proof of algebraic skills, etc. So all these things come in. If we think now, if we think about the actual question, going back to the original question that started this off, we're after the velocity of the spring after 1 second. So we what to do now is just let t equal 1 second. So going back to this problem, when t equals 1 second, ds by dt, the rate of change of displacement of time, or the velocity, equals e to the minus 0.9 times 1, which is just 0.9, 20 pi cos 10 pi, t is 1, minus 1.8 sine 10 pi. So looking at this function, we can see that the cosine of 10 pi is 1. Sorry, 2 pi is 1. So therefore the cosine of 10 pi is 1, so that cancels to 1. And the sine of 2 pi is 0, so the sine of 10 pi is 0. So the whole lot comes down to this. And we get the answer of 25.5 meters per second. Just as a little exercise, key this into the calculator and confirm you get the same answer, please. So e to the minus 0.9, 20 pi cos 10 pi minus 1.8 sine 10 pi, and see what you get. if you do this on the calculator and you get 21.42, it's because you're in degrees, not radians, okay? So therein lies a lesson, okay? It's worth thinking about this business here, because then you wouldn't have fallen into that trap. But the second thing to come out of it is, if you're working with radians, and you're always working in radians generally in these sorts of questions, you certainly are if you've got pi in the angle, then you need to check your calculus in radians, otherwise you get the wrong answer. So beware, okay? Right.